My friends, good evening. Qantas Flight 72, which occurred in October 2008, has often been compared to Air France 447, which would happen a few months later. Air France 447, the Rio-Paris flight. It was June 1st, 2009, so just 8 months after the accident I'm talking to you about today. The two accidents, actually, the two events, have nothing to do with each other, even though in both cases we're talking about an Airbus A330, the Air France 447. It was a problem with the sensor that was made worse by the fact that it was nighttime. The guy who was at the controls overreacted a bit and caused the stall. In the case we're interested in today, Qantas 72, it's a plane of the same type, an A330, whose computers suddenly thought so while it was cruising in broad daylight. No turbulence, nothing at all. The probes didn't freeze. The probes never sent any false information, but suddenly the fly-by-wire control system thought that the angle of attack had gone up to 50 degrees. Just like that, out of nowhere. This triggered stall protection mechanisms that shouldn't have been activated. But they were activated because they were fed by a false idea of the angle of attack. And this ended up causing an extremely abrupt nosedive of the Airbus A330. So you can imagine, the plane is flying like this at flight level 370 cruising altitude. People, for the most part, didn't have their seatbelts fastened. There was no turbulence, nothing at all. It was just normal life. And the aircraft was coming from Singapore to go to Perth in Australia. It belongs to the Australian airline Qantas, and suddenly, brutally, without any particular warning sign, the aircraft suddenly nosedives. So it goes into a sudden dive, and what happens is that it ends up at an 8-degree nose down angle. The number of jets is minus 0.8, so minus 0.8 jets. That means the plane was in weightlessness. It means the aircraft had almost no jets left, right? And so people floated in the cabin. Some hit their heads against the cabin ceiling. And then afterwards, when the captain took the mini control, he pulled on it to bring the aircraft back to level. Well, they fell back down abruptly. Out of 315 passengers, 119 were injured, many seriously, which is why the Australian authorities classified this event as an accident, even though the plane technically did not crash. The accident report is extremely thorough, over 300 pages, and quite difficult to understand. And today, there's someone from Patreon who gave me a chart with the challenge to make this video. So I took on that challenge, and I'm going to explain what happened and why. The Airbus system suddenly thought that the angle of attack was 50 degrees. And so afterwards, once they think this, well, there's a chain reaction that will be set in motion. And then who will actually cause this problem? The pilots then declared a mayday and managed to land. The plane had switched to alternate law, so it lost some of its protections. They managed to land, and they were met by firefighters, ambulances, all of that. Many people were evacuated, and the aircraft was later repaired, and then it returned to service. It's a problem that has never been fully explained. That means up until now, the Australian authorities, nor Airbus, nor anyone else, know exactly why what happened. I'm going to explain to you some mechanisms that are very deep within the Airbus system, which help us understand how messages are exchanged. That means how information like speed, angle of attack, and altitude circulate within the systems. And how could there have been a collision between this data so that an altitude of 37,000 feet was interpreted as an angle of attack of 50 degrees? Because that's really the big question. How? At 37,000 feet, the system suddenly believed it had over 50 degrees of angle of attack. These two values, 37,050, appear different. Yet, if we look at the protocol used in the Airbus, the aeronautical radio, incorporated 429, we realize that these two values are still associated in a certain way. And this shows that at some point there was something, probably the processor of one of the data computers, one of the air data computers, which started mixing up the information. And this sent it down the chain, right? It sent incorrect data and so caused this reaction from the aircraft. The accident report says that this event could not have ended with the complete loss of the Airbus. That means it couldn't have ended with a crash into the water. Yes and no, technically they are completely right. That's true. You'll see in the second part of the video in front of the board, you'll see that there are indeed limits. All of that led to what happened? The plane doing that and injuring people. That was the maximum we could get. There was no way to do worse than that. On the other hand, nothing forbids it. Let's imagine the same scenario. Let's imagine a similar scenario. And that's why we brought it closer to Air France 449. Let's imagine the same situation happening at night in a turbulent environment, maybe with less experienced pilots. And then they lose it. They see the plane, quote unquote, doing anything, and they themselves will overreact. And so they could actually cause the stall. As I told you, the plane had switched to alternate mode, which means it no longer had stall protection. And what if these pilots at 37,000 feet, so at a time when they had less aerodynamic margin up and down, had started to overreact at the controls? They could have caused a stall, except that here, since it was daytime, the conditions were better. Indeed, the aircraft was able to be recovered and it landed, even though it still went through quite a lot. Several times, it made some pretty frightening and impressive dives. So there you go, my friends. In a minute, we'll move on to the second part of the video. Let me remind you, please show me that you like my work by subscribing. I checked the statistics. More than half of the people who watch my videos aren't subscribed. So please subscribe. It doesn't cost anything. It's free. Some channels spend half their time just explaining why you should subscribe. I rarely do that, which is why my subscriber count is stagnating. So please subscribe. Some of you can also subscribe on Patreon to see the few videos. I release 1 or 2 videos a month that are exclusive to Patreon subscribers. Thank you for watching this first part, and we'll move on immediately to the second. I'm thinking about how to start. So what we're going to do is talk about the Aeronautical Radio Incorporated 429 protocol. Aeronautical Radio Incorporated is an organization that was created around the 1920s. They worked with Morse code, telex, and signals in general. In the 1970s, they created the Aeronautical Radio Incorporated 429 protocol, which is still in use today on both Airbus and Boeing planes. When you get down to this level of detail in the protocol, why difference between Airbus and Boeing, and even other airliners or even fighter jets, this video that explains this protocol, it's the only one, as far as I know, that exists on the internet, however long and drawn out it may be. It lets us dive into the details and understand why. There was this near loss of control on the Qantas 72, the Airbus A330, which injured a lot of people. So the idea behind this Aeronautical Radio Incorporated 429 protocol is that it allows different systems in airliners to communicate with each other. So what happens is that we have, for example, you can imagine in an Airbus, we have an air data computer. Actually, we have a box that contains 2 computers inside called Air Data Inertial Reference Unit. It's a box that manages inertial parameters on one side and R parameters on the other, but they're both housed together even though we treat them as 2 separate computers. So imagine a computer that will calculate, for example, longitude, latitude, ground speed, wind speed, and another one that will evaluate or calculate the aircraft speed, Mach number, angle of attack, all of that. They also need to share this information with other systems. How will they do that? They are going to use this protocol. This protocol works like this on the hardware level, on the physical level. You have a pair of cables that will come out of the transmitter and will be distributed to the receivers. You can have up to 20 receivers per pair of cables, but there is always only one transmitter in a pair of cables. So what happens is that our transmitter sends messages that are picked up by those who need them, who will receive them on this line. So we have a channel for transmission. And if feedback is needed, the feedback won't go through the same wires. Other wires will be needed. So one of the criticisms that can be made of the ARINC 429 protocol is that it is very demanding in terms of electrical wires. It was created in the 1970s when less data was needed than today. So now there's an excess of electrical wires. And that's why in its latest 777 Boeing decided to switch to ARIC 629. That's another protocol, it's another variation, which uses a bit fewer electrical wires, but works pretty much the same way. So what kind of messages are in those wires? What kind of messages are there? So there are messages made up of a series of 32 characters that can be either 0 or 1. What we call in computer science bits, bits. A bit, if you want, can only have two values, 0 or 1. All right, simply put, it's an electrical signal. And then we're going to inject a signal, and it will go one way to signify 1, and it will go the other way to signify 0. You see, we're in a binary logic when we get down to this level. And that's why everything, no matter what value we have to process, we always have to reduce it to 0s and 1s. So does the word always have 32 bits? 32, so 4 bytes. Yes, 4 bytes, 32 bits of 0s and 1s divided into 5 parts. So we're going to have our word. I didn't draw all 32 boxes, but you get the idea. We're going to have 5 parts in there. The first one is a tag. It's a label if you want. It's a tag. What's the tag? The tag takes the first values. The first 8 positions, right? So they're 0s or 1s, aren't they, etc. The tag occupies the first 8 positions. The tag is a value. It can go up to 256. It's a value that will define what we're talking about. What's inside this word? Why? Because when you take, for example, an air data computer is capable of transmitting a lot of information. So for the receivers to know what it's sending, what it's going to do is put a label. For example, when it does, that's a convention that varies by aircraft manufacturer. Everyone chooses what to do. In fact, for example, if it's going to send the altitude, it will use the number 131. Label 131 means altitude, indicating that the following data is about altitude. For example, if it wants to send the angle of attack, it will use label 161. Label 161 means what follows. It's angle of attack information that I'm giving you. So what we're going to do is this is an 8. After that, we'll take the next 2 positions. There are only 2 next positions here, and that'll be the origin. Okay, so it was at 10, so it'll be 9 and 10. So this is the origin. You can have ADRU 1, 2, or 3, and you also have the option to select 1, 2, or 3 here. And actually, at that point, it will define who it is. Okay, so now what we're going to do, the rest is here. We're going to look at the data part, the data, really the value that we're sending. So after that here, we're going to go up to position 30, and then what we have left, we have this left here. 2 positions. We'll put them in instead. We'll go up to position 29, okay? Then we'll have 30 and 31. That'll be the status, okay? It's something we can put in, different values. Here's the last point, parity. The 32 end one is called parity. So what is parity? It can be 0 or 1 like these boxes. And actually parity, it lets us verify the message's integrity. The message, this entire message, which is made up of 0s and 1s, a series of 32 zeros and ones must always have an odd number of ones. So the receiver, when he gets it, the first thing he's going to check is the number of ones in it. If he sees that there's an even number of ones, he's going to reject it as invalid. So how do we do parity? It's very simple. We're going to go all the way up to box 31. With the methods, he counts how many ones there are at this point. If at this point there's an even number of ones, parity will set it to 1. That way we get to a number. Odd. If there is already in the first 31 boxes, there is, let's say, an odd number already. So what are we going to do? We're going to put 0 in the parity. Parity allows us to check, to some extent, if the message is intact. But you realize that it's not perfect because it can protect us. For example, what we call a bit flip, it means that, for instance, due to some error, it could be interference, cosmic radiation, or a hardware defect. It doesn't matter. You can change a 1 to a 0 or vice versa, which creates incorrect parity. But you realize that this isn't something that will protect us against multiple errors. If several values are altered by a runaway event, hardware or something else, parity can, in 1 out of 2 cases, be completely correct. All right, so this is our word. So the words are sent. The sending speed of the protocol is 12.5 bits per second. So we're going to send 12.4, actually 12,500 bits per second. Or the other fast standard is 100. It's 100,000 per second, and each manufacturer can, depending on their needs, vary these speeds by 33%. So you can be 33% below, 33% above, same here. So technically we can go up to 133,000 bits per second, so it can be extremely fast, as you can see, especially for values that are more or less several times per second. And when systems process and handle many values, I think the DRU on the, don't quote me on that, I'm not sure about my number, I think it uses 46 or 47. Let's say about 50 values that are over there that it has to send in, that it has to send to the other systems. And this, for some of them, several times per second. You see? So you see that you'll use that up very quickly. So you'll need to keep up the speed, all right? So equivalent to 4 bits, then you have another word and so on. If a system has nothing to send, it transmits empty words. 0, 0, 0, 0. If a system misses 2 words, it's considered, you have the flag that comes out, it's considered as down. That's basically how the systems work. Now, we're going to go further, and what interests us today is how to give them are encoded, how we're going to encode the data. We can't simply use 0s and 1s to encode any number we want. That doesn't work. We'll have to find a system, and here you'll see that the ARIC system has a very clever method to encode this. What I'm going to do is erase all of this, okay? And then I'm going to write some numbers, and that will let you see why I set up the table vertically. So here we have an altitude encoding. So how is the system going to encode the altitude, and how will the others receive it? So by convention, when it comes to altitude, all systems will have some kind of scale, which goes from 1 up to 65,536. Each number was obtained by multiplying by 2. 64 doubled is 128, then 256, and so on. So now, how are we going to determine the altitude? How are we going to do it? We're going to do this. We're going to take, I'll try writing with the glass, hoping it's visible. We're going to try to use 0s and 1s to turn these numbers on or off. Look, I'm going to bring a calculator so we can all be on the same page. So here's the idea. Let's imagine, for example, that I have to write 37,000 feet because the Qantas plane was flying at 37,000 feet. How will we encode 37,000 feet with this method? So what's going to happen is that we're going to use 0s and 1s, 65,000 and something, too big. We're not going to use it, it's too big. We'll take 0 here, the green isn't clear, so I'll use blue instead. There you go. I don't need to take 65,000. It's already in the protocol and system. But you won't see these days an Airbus flying at 65,000 feet. So it's not something we need. The story value will always be 0 now. 32,768. Interesting. I'll take it. There you go. So I have my R. After 16,000, add 32 and 16. Oh, that'll send us way past 37,000. I clearly don't need it. When doing mental math, in this case, I don't need to calculate the exact value. I just need to know, does it go over 37,000 or not? Obviously, it goes over 37,000. So I put 0 after 8,192, 832. We're at 40000 now. What I'm going to do is 4030. Now this is interesting. So here I take OK, right? I'm combining 0s and 1s to form my altitude. Next, now, what I'm going to do is take the calculator. So I take 32,768 plus 4,096, that gives us 36,864, okay? 36,864 minus 37,000 equals 136. So we're short 136. We're 136 short of 37,000. What's the easiest way to express 136 with the fewest digits? By taking the highest digit, so 136, we'll take 128. And we'll take the 8 here. There you go. And everything else. Everything else will, of course, be 0. But, all right, and this, it's 0. So, you see that with this, we've made 37,000 feet. When 37,000 feet shows on an Airbus A330 or Boeing altimeter, in reality, somewhere, it's an air data computer that sent a 32-bit word, which includes the first part, the label. Let's say that's altitude. Then it sent 100 digits, right? For example, I'm air data computer 1. It sent this sequence. Everything, like that. It sent a status, then parity. That's 37,000 feet, okay? So you see, it's pretty simple. You can have fun. You can write this down with a pen and have fun calculating whatever numbers you want. For example, what is it made up of if there are 512 feet? I put 1 here and 0 elsewhere. That's enough. If it changes to 512, it drops to 511. I'm putting 0 here and 1 everywhere else. Because if you actually take, what's nice is if you take, for example, let's say you're trying to get 16,383, that sums up everything present. You place 1s everywhere, then 0s after that. If you go up one step, do you set everything to 0 and put a 1 there? If you go up to 16,385, it's simple. Just put a 1 here and a 1 there. You take a step, add another, put a 0 here, a 1 there, and continue. You see? You can pretty much make up any altitude you want with this method. There you go, okay? So it's an extremely clever method. Now here's a problem. There is a problem. Because if there wasn't a problem, we wouldn't have had more than 100 people injured on that plane. And all the aggravation, right? So that's what happened. When the Australian investigators started trying to understand, to analyze the false incidents that appeared, they realized that the false incidents, also the speeds were inaccurate. But I'll just explain the principle to you with the incidents, but with speed, it's exactly the same principle. So they noticed something. They noticed that it wasn't random, that these were very specific values, and they tried to understand how they were generated. And something in particular struck them. They noticed that when they were at 37,000 feet altitude, the angle of attack value that was generated was 50 degrees. That's 50 degrees and a bit. And they thought there was a correlation between 50 degrees and 37,000 feet. When the plane was at 37,000 feet, the false angle of attack that was generated was 50 degrees. As it began descending, there were additional spikes. Those 50 degrees were unique. They started asking themselves, what could have happened? So let me tell you. I'm going to use another scale now. The other scale is the scale of the incidence calculation system. Because when our receiver receives the altitude, how does it know the altitude? There's a label 131, as I mentioned earlier. It's coming. Then it says, it's altitude. So it uses that reading grid. Then it will use the zeros and ones to determine the altitude. Now, let's imagine it receives a label 161, which means angle of attack. It's going to use another scale, a scale that's formed in the same way, which starts at 0.044. And then we multiply 0.044, then we get 0.088, and we go up to 90 degrees. So here's what we'll do. I won't go through it all, but you get the idea and can work it out yourself. Look, if I take here, that's altitude, right? This is altitude. But if it's about angle of attack, we're going to use another way of looking at it. The highest value is 90 degrees. What's the value below that? It's 4518 divided by 2. So here it's 45. 2 wars. Half of 45 is 22. 0.5. Half of 22.5 is 11. Comma 25 half of 11. I'm not wrong. Yes, I'm not wrong. That's correct. Half of 11. 0.25. How much is that? It's 5. Comma. So 125, that's 6. That's 2, something like that. All right. So I can still go on, right? I can still continue and I'll get smaller and smaller values and eventually I'll reach 0. 44, okay? So what I'm trying to explain when we look at this table is that what obviously happened is that we had the wrong grid that was used to read. The wrong grid was used. That means it's as if we took the altitude value and said, this is an incidence, and we use the incidence grid to read it. And if you look at 37,000 feet, what does that give you? That gives 45 plus 5. And there, that makes 50. 62 degrees and some decimals. When you arrive, the numbers are very low, extremely low. So that's where the 50 degrees come from. So that's what we did. And then you realize that it's not a probe problem. The probes were fine because many people compared this accident to Air France 447 since it happened a little earlier. They said, yes, it's likely the same story. The probes, no, they're unrelated and working normally. In fact, it's one. It's a completely crazy story because what we have is a number from the reading grid. It's as if this happened. Our system received a word, okay? This word contained in data the altitude, but in the label, it contained the angle of attack. That means it's as if we did this. It's as if we had, imagine this, a word like this if we had. Here, we're going to put in the label the tag. We're going to put 161 by mistake when we should be putting 131. We put 161. You see, that's wrong. Here, we put 1 for the ADRU, 1. And then here, what are we going to put? We're going to enter an altitude value. We're going to enter that. That means what you're seeing here, 0, 1, 3, 0, you see? 3 more, 0, 1, and then 4, 0, etc. You see? So we inject, we're creating a Frankenstein. Actually, the label has 161 incidents, and then we put the altitude data inside, and that's when it creates that famous spike. So what should I note? Maybe I should erase something, but actually I don't need to. I can still write here. Look, one of the issues, who allows it? Because the Australian investigators tried everything to explain. They understood that, so they saw that it happened, but why did it happen? From that point on, it's a complete mystery. There are some clues, there are some assumptions, but we've never managed to reproduce the problem, even though we know it's a problem that happened across millions of flight hours, carried out by Airbus, carried out by these ADERU. Well, it's a problem we've seen 3 times. You see what I mean? So go and find that. It's the needle in a haystack. So it's literally a Markov jump, like I mentioned in one of the videos, the Markov jump. It's visible in the 777 crash video by British Airways at Heathrow Airport, where both engines failed completely out. And you know, it stalled during landing. It touched down just before the runway. This interesting video shows examples of Markovian jumps. Watch it. It means cases where we have something so improbable that we consider it impossible, something we can't even imagine. It happens someday, okay? Here's something important that could be a clue since we mentioned Frankenstein. How do you make one? Like this?
Yeah.
If you take your phone or your computer today, you're probably using technology. 64 bits, okay? Why? What does that mean? It means your system is able to handle it all at once. Whether it's the processor, the memory, the software, all of that is able to handle 64-bit words all at once, okay? In the past, 12 years ago, 10 years ago, 15 years ago, what kind of systems were there? They were systems that worked in 32 bits, right? They were only able to handle 32-bit words, so twice as small, okay? But if we return to the design phase, for the Airbus A330, we're at the beginning of the 1990s. It was designed most likely in the 1980s. We primarily used CROA technology and worked with 16-bit systems. So when you open an ADRU, the processor, the memory, all that works in 16 bits, okay? And the word I'm talking to you about, corresponding to ring 429, what is it? Are they 32-bit words? Do you see the problem? That's a huge problem because we have 32-bit words, we keep making them. We make thousands of them per second. The problem is the system can't handle them. So what are we going to do? We're going to do this. I'll erase and I'll show you what we're going to do. So we take our word, it's 32 bits from 1 to 32. That's our term, that's our data unit or information. We can't fit it in, we can't process it as a single block. What are we going to do? We're going to cut it in two. We're going to cut it into two pieces. So here we have 16. What about 16 here? We're working with 16 bits, right? And that matches our architecture. So here we're aligned with our architecture. And so we're going to store them in memory in two different locations because our memory, with 16 bits, a 32-bit word can't be stored at once. So we split it in two and store each part separately. Now realize this. Which one is first? Which one is the first? The first piece, it's the label tag. You can see that the tag it's only on one piece. And here we're going to have, like I said, the origin data parity here, OK1 or 0, for example. And you can clearly see that the label is stored in the first piece and it's stored with a part of the data. I write data like this. Look and see what I'm doing on the other one. Why here? I write small here, big there. Because when you look, remember the scale from earlier? Well, it's less significant than that, because if you remember the factors that were growing exponentially, it's exponential. It kept doubling, and each time you noticed it. What's on the right is much more important than what's on the left. That's just a detail. What's gonna happen is that the risk is we rearrange a piece, okay? A piece, once we put everything back together with another one. Sorry, we combine it with another piece. The glass is nearly invisible. And we make another Frankenstein. We make our word here, which is Frankenstein, which comes from two different words. So of course, parity can tell us that it's wrong, but it only works one time out of two, because maybe you take here, you take here. A missing piece had an odd number of 1s and was replaced with another piece also having an odd number of 1s. It works very well. You see what I mean? It works very well like that. So the parity won't be an indicator. You see what I mean? So that's really boring. Now the other one, the other question is, why did our system, our primary flight computer, why didn't it realize there was a problem? It got a spike, right? Bam! The angle of attack, which was low, suddenly jumps to 50 degrees. But why didn't it do anything? Why didn't it understand there was a problem? Actually, it does understand there's a problem, except that in this case, it was a little bit limited. Let me tell you, I don't have my model here. I should get it. You see, this is video. It's actually pretty complex. And you realize that you saw that when we talk about Airbus, we're always there. We're always dealing with numbers, algorithms, zeros, ones, all that, electronics and everything. When we talk about Boeing, we mean oil, fuel, cables, pulleys. It's a completely different world. So look at the story. Our system, yes, it's programmed to detect spikes and to disregard those spikes. But to a certain extent. The problem is that it was exceeded in this case. How? I'll tell you soon. At first, on the Airbus, there are 3 angle of attack sensors. 1 on the left, 2 on the right, close to each other. 1 on the left, 2 on the right. So at first, people wondered, how do we know? What if a malfunctioning angle of attack sensor gives false readings? All right, let's do this. What we're going to do is take the average of the 3. And then, if one of them deviates from the average by a certain value, we're going to set a value. We'll say we won't tolerate more than that. If it deviates from that value, well, we won't take it into account. So they had a problem with this approach. On paper, it seems great, but in reality, it has issues. It's that since physically probes 2 and 3 are located on the right side of the Airbus, in some cases like a skid or poor rudder input, for example, the right side probes can temporarily display incorrect values since they're in the same location. They'll override probe 1 on the other side, which displays the correct value. Probe 1 will be skipped and probes 2 and 3 display wrong values. Do you see what I mean? So it was still a hassle and a problem. So what did they decide to do? They decided to change the algorithm a little bit to do this. We measure the 3 incidences, okay? We take the 3 incidences, we sort them, we take the median value, okay? It's the middle value, not the largest or smallest. We can sort the 3 if needed. After that, what we're going to do is we're only going to average the first and the second one, okay? We'll average the first and second values and compare them to the median. After that, if the value we use, the one we're going to send to the flight control computer, if we're going to send it this value, as long as we have consistency with the median value of the 3 and the average of the first and second, you see? So there's a subtle difference compared to the system. Here's the problem. What should we do? If suddenly the incidence value deviates, what if there's a deviation after all? If probe 1 or 2 suddenly deviates from the median, what should we do? So we do this. If there's a deviation value, we will do that. For 1 to 2 seconds under subtiling ST 501 subtiling ST, (501). At Airbus, we decided that since it's a plane that moves, it's dynamic, all that, we can allow ourselves as much as possible to remember a value for 1 or 2 seconds. So we can use the value from 1 or 2 seconds ago, and we consider over this period of time that it's not a combat jet either. Its angle of attack will stay about the same, but after a second or 2, action will be needed. That's the main point. Secondly, the verification mechanisms in the air data computer, that's 501, it usually detects malfunctions or errors within 1 second. And so normally what do? We stop taking values for 1 or 2 seconds, and we have to get back into the loop later, hoping that if a problem occurs during that time, it will have been detected and the air data computer removed from the loop. You see what I mean? That makes sense. Now, the problem is how we get back into the loop, because after just a split second, you need a value. You need a value that's reliable, because normally, just so you know, we measure this incidence and give it to the system 25 times per second, you see? We need it all the time, 25 times per second. It's sent. So it's very fast information. It has to be updated constantly. And there, if for 1 or 2 seconds we have it, but we don't update it, you see, it's like we've missed 30 updates anyway. So we need to update it, but how do we do it? Returning into the loop is always risky in this algorithm, because if we go right back into the loop and we do our comparisons again, imagine if we discover another delta at that moment, and that the conditions that made us refuse to take the values are still present. What will happen? Well, we can't take them again. And we're going to stay stuck with a false incidence value, potentially for 10 seconds, 15 seconds. You see, it was rejected. So what did we do? We decided that At the end of the 12-second waiting period during a single cycle, by 25, a single cycle, we're going to take the values as they are. We're going to take them, the values as they are. And in this case, we take them, we have to consider them as valid. And afterwards, we go back into the algorithm. Afterwards, we start over and all that. The problem is that with this, if I have spikes, look, the system finds the wrong value. It's going to block. It gets here. That's my spike. What does my system do? My system, for 1 or 2 seconds, it doesn't take any new values. It gets right there. It sticks its head out to breathe. And at that moment, there's a spike that was exactly 1 or 2 seconds later. You see? And now it's going to swallow it. It's going to take it. Now it's going to take it. It's going to take it. And now we finish with an angle of 50 degrees. We end up with a system that thinks it's a disaster and that the plane is stalling. And it's going to start sending. So it's going to start acting on the elevator to make the plane nose down. Fortunately. And here we really have to tip our hat to Airbus. It's because since it's a company that's used to automation, they still created a limited authority. That means that when it started, when the protection system kicked in and began to push the nose of the plane down, it had limited authority. Whereas what crashed with the maneuvering characteristics augmentation system, what crashed the Boeing 737 MAX, is that the maneuvering characteristics augmentation system had unlimited authority. Boeing should have recruited engineers from Airbus, but they didn't. They're not used to building protections or automated systems at that scale. So when they developed the maneuvering characteristics augmentation system, they aimed to add a safeguard. Well, they completely messed up. They made a beginner's mistake. Really a mistake someone makes when they're building their first automatic thing, you know? And they gave maneuvering characteristics augmentation system total unlimited authority. And then, of course, 2 planes crashed, Lion Air and the other one, Ethiopian, which are the 2 that are covered. Isn't it on this channel? So there you go, my friends. I hope this has been clear, really. Right now, you see, I have doubts suddenly. You see, I'm seized by a terrible doubt. Was it clear? Let me know in the comments. But now we're really starting to see why this plane went into that dive. And in the same way, exactly with the same logic, they found that the number of macaques increased. That the speed at one point showed 1,000 knots. You see, 1,000 knots is 1,000 miles per hour, which is about 1,800 kilometers per hour. I mean, you won't see an Airbus reach that speed. And yet, that's what they had. That's what they saw on the display. That's what the system thought. That's why they sometimes had both overspeed and stall alarms sounding simultaneously. Overspeed stall, it was non-stop. Fortunately, these pilots, who were very experienced, didn't pay attention to it. It's true that it's unsettling, but they still managed to control their plane and to land it. So there you go, my friends. Thank you for watching this video until the end, and I'll see you in the next one. See you very soon.